Okay, today we're going to talk about the sun, chapter 9. Here's a picture of the sun as we all know it. It's a happy place, as evidenced by the happy expression on the sun. Okay, you know that this is not the sun as we know it, obviously, because the sun should be yellow. So here's the sun, the yellow sun. Now here's the sun as we know it. Just a hot orb, very difficult to look at. Probably shouldn't look at it without some kind of filtering. What do we know about our sun? It's an average star, which used to be, kind of perplexing to me. I always think you want to be the best at something if you can, but our sun is actually just a mediocre star, and to be honest, that's a good thing because it allows life as we know it to exist. If our sun was a more luminous star, then the radiation would be too much to have life as we know it, and vice versa. If it were, say, a red dwarf, then we wouldn't get enough radiation. So being a mediocre star is a good thing for life as we know it. It is 8 light minutes away, so the light that we receive is 8 minutes old. It was sent by the sun 8 minutes ago. We don't know what happened to the sun in that 8 minutes. We'll know within 8 minutes. But it's the closest star to us. The next nearest star is 4.2 light years away, which is Proxima Centauri, which is the small neighbor of Alpha Centauri. And as we said before, if we were to envision the Earth-Sun distance as 1 meter, then Proxima Centauri would be down in Montgomery, Alabama, in relation to Decatur or northern Alabama. So 4.3 light years away is a long ways away. So anything we're going to learn about stars, we better learn the most of it from our own star, the sun. It is the sole source of energy for the Earth, either directly or indirectly, making life as we know it possible. Here's a real look at our sun, along with sunspots. Diameter of the sun is about 100 times the diameter of the Earth, so the Earth in relation to the sun is very small, as we can see here. In fact, this is not even the right perspective. The Earth should be 1/100th the diameter of the sun, so it's this little blue dot in relation to the full sun here. And 100 of those blue dots would fit across the diameter of the sun. That's how big the sun is in relation to our Earth. So the volume of the sun, since the volume goes as the radius cubed, the volume is about 100 cubed, or 1,000,000 times larger than our Earth. 1,000,000 Earths, 1,000,000 Earths could fit inside the sun. Just for fun, we would note that the Earth's distance is about 100 times the diameter of the sun. So to put this in perspective, 1,000,000 suns would fit inside a sphere that had a radius equal to the Earth-Sun distance. And that would be the same kind of perspective as the Earth compared to the volume of the sun. Here's another look. Here's the Earth, this little blue orb here, compared to the sun with a solar flare extending out. Hence, this flare would totally engulf the Earth if the Earth were that close to the sun. It would destroy the Earth. Mass of the sun is 330 times the mass, 30,000 times the mass of the Earth. So it's about 1/3 of a million times the mass of the Earth, making its average density 1.4 grams per cubic centimeter, which is just a little bit more on the average than the density of water. There's a similar density to Jupiter, so maybe suggesting a similar composition between the two. And about 1/4 the density of Earth. Earth is about 5.5, 5.6 grams per cubic centimeter. Every once in a while, Mercury transits the Sun in front of our view. In other words, it eclipses within our line of sight with the Sun. And here's one of those transits of the Mercury across the Sun. This happens 13 times per century, Mercury being the closest planet to the Sun. And it actually looks bigger than it actually is in relation to the Sun here, because it's actually 0.4 astronomical units away from the Sun. So the fact that it's closer to us makes it look bigger in relation to the Sun. Venus also transits the Sun once in a while, and the last transit of Venus was in June of 2004, and here's a video of it as Venus was transiting across the Sun. Again, Venus looks bigger than it should because it's much closer to us. It's 0.7 astronomical units away from the Sun, hence giving it a larger appearance as it moves across the Sun. Here's another picture of that latest transit of Venus back in 2004, and evidently there's an airplane about to cross over that too. In order for Venus to transit the Sun to our line of sight, it must be crossing an orbital node at that moment in relation to the ecliptic plane, and be at inferior conjunction with respect to us. So it must be in our line of sight and also crossing in our line of sight across the ecliptic plane. That doesn't happen too often, because even with everything near the ecliptic plane, it's kind of off the ecliptic plane a little bit, and so are we. So to have those both happen at the same time happens very infrequently, and in fact it happens in time intervals of 8, 121.5, 8, and 105.5 years. So in 2004, it hadn't happened for about 121.5 years before that, and fortunately we're in the 8-year cycle now. So the next time Venus will transit the Sun will be in the year 2012, actually in June of 2012, and after that will be 2117. So we'll have to wait a long time after that. So I'm looking forward to 2012. Here's that airplane. Evidently there's a lot of air traffic on Venus. Just kidding. Here's a video of the Sun actually turning, and we can see sunspots moving across the face of the Sun. And if we were to actually plot the time it took for those sunspots to go across from our perspective, we could actually figure out how long it takes for the Sun to turn on its axis. And it turns out that its rotation period is 25 days, Earth days, at the equator, and 31 days at the poles. So there's a differential rotation of the Sun. The equator rotates faster than the poles. The Sun radiates energy at a rate of 4 times 10 to the 26 watts. That's joules per second put out by the Sun. Most of that energy goes in three-dimensionally in all directions. Only a little fraction of it actually makes it our way towards the Earth. But this amount of energy, this 4 times 10 to the 26 watts, is equivalent to about 100 billion, billion being 10 to the 9, so it's about 100 billion 1 megaton nuclear bombs blasting off per second. 100 billion. I think the population of the Earth is 6 billion people, then that is about 16 times the population of the Earth. That many nuclear bombs going off per second is the energy of the Sun. A fraction of that reaches us, and that is the solar constant. The amount of energy that reaches us per cubic meter is 1400 watt seconds per cubic meter. A watt second is a joule, so we get 1400 joules per second per meter squared hitting the Earth, and that is called the solar constant, the amount of energy. And that's pretty important for life as we know it, because that constant influx of energy is responsible for the consistent growth of life on Earth. And if we didn't have this consistent energy inflow, then life as we know it could not exist. We know that the life on Earth is very dependent in terms of its ecosystem development, so it needs a consistent influx of energy, and that's what the sun gives us. Here's the sun. If we were able to look inside the sun, we would get an overall structure of the interior of the sun. And here we would see that there's a core, a radiative zone, and a convective zone. The central core is where the nuclear reactions take place, the actual conversion of energy, or conversion of mass into energy, occurring at the core. Then we have a radiative zone where energy is transmitted by radiation. It's a lot of ion-type particles in what is called a plasma in that zone that cannot absorb that energy, so it's just basically radiation. And then there's a convective zone towards the exterior of the sun, where there are a mechanism to absorb radiation, and hence energy can be transmitted through the actual movement of matter, which is convection. Here's our sun, enhanced here along with its atmosphere. It must be a very hot place. Of course, it's a very hot place. So if you had the sun, it would be a good thing to look inside and see what is responsible for that heat. As we see here, we've got the core, the radiation zone, and the convection. And then we have the atmosphere of the sun above the surface of the sun, which is the photosphere. Photosphere is the yellow surface that we see. It's about 500 kilometers thick, which is about 300 miles. It only represents about 0.1%, 1/10 of 1% of the sun's total radius. The chromosphere is the first layer of the atmosphere, just above that, the lower atmosphere. That is about 1,500 kilometers, or about 900 miles in thickness. Then we have the transition zone, a region of rising temperature just above the chromosphere and transitioning to the corona. And then we have the solar corona, the outer atmosphere, which lies above the transition zone, about 10,000 kilometers above. And finally, we have the solar wind, which is the particle matter extending outward from the sun, the radiation from the sun, and the protons and helium nuclei and electrons being thrown out from the sun. We call it the solar wind, and that actually extends out through our solar system. So the extent of our solar system is the solar wind. Looking inside the sun, the density of the sun is very compact towards the center. The center of the sun is 20 times the density of iron. It's under great pressure, great heat. This allows the solar fusion to take place, which is an important environment to allow that to happen so that we can actually have a sun. And so we have 20 times the density of iron in the center, and then it drops off pretty rapidly towards the surface. At the surface of the sun, it's only 1/10,000th the density of air, and air is not very dense as we know it, but the surface of the sun is even less dense than that, 1/10,000th the density of air. Temperature of the sun, very hot towards the center. The surface is 5,800 degrees Kelvin, which is pretty hot, but not any hotter than the center of our own Earth. That's about 10,000 degrees Fahrenheit. The center of the Sun is 15 million degrees Kelvin, 27 million degrees Fahrenheit, and we need that kind of heat to create the conditions that will allow fusion to take place. So it's almost a if and only if we need this kind of heat for fusion to take place, and fusion will also fuel that kind of heat. The Sun is a very interesting balance between this energy mechanism that's creating pressure, which is forcing material and energy outward from the center of the Sun, and gravity, the great mass of the Sun, being pulling in by gravity. At some point, if time has been allowed to take place and the two have been working against each other, at some point there will be an equilibrium established where the two forces have balanced. So pressure is pushing out, gravity is pulling in, and if there is a steady flow of this pressure and gravity pulling in, then we have this sphere, which we call the Sun. So it's a stellar balance between the two. The Sun also undergoes solar oscillations. These oscillations are pressure vibrations that ring through the Sun like a bell. The oscillations help give us information on the interior of the Sun, just like earthquakes would give us information on the interior of the Earth. We study these oscillations to figure out what's happening to the interior of the Sun. And these are studied by the Global Oscillations Network Group, otherwise known as GONG. The study of the interior of the Sun is called helioseismology. And with the study and this analysis, we come up with the standard solar model with this pressure versus gravity equilibrium balance, and then these vibrations occurring through the Sun. The solar model accurately predicts the frequencies of oscillations to 0.1%, which is an incredible achievement for any kind of model to be that accurate. Looking at the interior of the Sun, the main mechanism of the energy release is nuclear fusion. Nuclear fusion in the Sun's core produces extreme amounts of energy and very high temperatures. We'll talk more about how this happens in the next lecture, but it's nuclear fusion that fuels the Sun. The high temperature separates atoms into nuclei and electrons with no particular normal atomic structure. So when they are released and separate like this, we call that a plasma. We have these charged particles. They're interacting both by gravity, but mainly by electromagnetic repulsion and attraction. And so we have this new kind of matter, this fourth kind of matter called plasma. 99% of the universe is this fourth kind of matter that we never talk about in everyday life called plasma. In relation to solid, liquid, and gas, there's plasma as well. Radiation passes unabsorbed through this plasma, because normally radiation is absorbed through the electron orbitals that might be in an atom, but if the atom doesn't have any electrons, doesn't have any orbitals, then it can't absorb that energy, so it goes right through this plasma to the convection zone. In the convection zone, the temperature is somewhat lower. We actually do have mechanisms that can absorb energy, like atoms with electrons, and hence they can actually absorb energy, hence the radiation can be absorbed, and hence the mechanism for transferring the energy from that point is more of a matter type flow, which we call convection. So hot matter actually physically moves then in this outer layer of the sun called the convection zone. We reached the sun, and we've reached the surface. At the sun's surface, the gas is too thin to sustain this continued flow of matter, this convection. It gets too thin, it's only 1/10,000th the density of air, and so at that point the extra radiation just radiates out into space, and that gives us the radiation that we get from the sun. So it kind of looks like this little diagram here. Thermonuclear reactions in the center, radiation through the radiative zone, convection, actual movement of matter, and then beyond that is the solar wind that extends out to us. As we look at the surface of the sun, we can see some granulation on the surface, some dark and light areas give it a granular texture on the surface. Here's a closer look. It's a direct visual effect of matter moving toward you and away from you. So granulation is a direct reflection of the actual motion at the top of the convection zone. In fact, the bright areas are hot matter that's moving towards you at a speed of up to about 1 kilometer per second. It's a great speed. And the dark areas is cooler matter that's moving away from you. So you have hot matter and cooler matter moving in a convective way, actual circular or elliptical way, as it's moving towards you and away from you, and creating this granular texture that we see in the sun. If we took a little area of this and blew it up so that we can see it more closely, we can see some of this granular texture, these grains that are on the surface of the sun, individual grains. Each granule is about 1,000 kilometers across, which would be approximately 600 miles across, and would last about 5 to 10 minutes. So these grains would last about 5 to 10 minutes, and then you'd have new grains developing. But 1,000 kilometers across is approximately about the size of Texas. There's about 1,000 kilometers across and 1,000 kilometers in height. So a grain is about the size of Texas. Here's a look. I think it's Mercury passing above the sun. It looks like it's right close to the sun there, but this is again from our perspective. So Mercury is still 40% of our distance away from the sun, but it looks pretty close in this picture here. We can see some of the texture of the sun in this picture, and we can also have supergranulation cells that can have granules even 30,000 kilometers across, much larger, just below the surface. Looking at some of that granulation again. What we know mainly about the aspects of the sun comes from spectroscopy. Again, the study of light. We've talked about this in an earlier chapter, but this is how we know just about everything that is beyond the Earth's atmosphere is from spectroscopy. And if we look at the solar spectrum, we can see a continuous spectrum with absorption lines throughout that continuous spectrum, indicating that there is a continuous source of energy, of light, creating a full continuous spectrum, and between us and that source is gas that is absorbing some of that energy. So a source behind a gas creates what we call an absorption spectrum, and that's what we see from the sun. The absorbed lines mainly identify what those gases are, and it's mainly, in terms of the sun, hydrogen and helium. So most of the absorption lines are due to the elements of hydrogen and helium. Here's the full sun spectrum that we would see, the Fraunhofer diffraction absorption of the sun. Hydrogen and helium make up 99.9% of the atoms that we see, but the composition changes at the core, and we can see indication of up to 67 elements in the sun, but 99.9% of it is either hydrogen. Part of the sun is the photosphere, the surface of the sun, and that is what most of the energy that we get, the peak of the energy that we get from the sun is in the visible range, which biologists would say that's why we are visually adept at seeing in that range, because that's what we have adapted to. If we need other aspects to survive, like if we need to see at night, then we'd be able to see in the infrared. And some animals can see in the infrared. We can't. But that's the range that we see, the visible range, corresponding from this black body radiation to a temperature of around 6,000 K. Above the photosphere is the atmosphere. The atmosphere of the sun consists of the chromosphere, which is the near atmosphere, the lower atmosphere, closest to the photosphere. Then we have the transition zone as we transition from the chromosphere to the corona. And here's the chromosphere. The chromosphere is the thin red section that just lies just above the photosphere. You can see these flares from the chromosphere area here. And we normally can't see the chromosphere. It's normally not visible because of its low density and the brightness of the photosphere right there. So about the only time you can see it is when you have a solar eclipse. The moon eclipsing the sun, so they can block out the photosphere, and hence we can see the chromosphere. The SOHO satellite that looks at the sun has its own little eclipse type measure that will block out the sun so they can look at other aspects of the sun's atmosphere. Here's a look at the chromosphere. Just looking at the hydrogen alpha lines, we can look at the chromosphere because that's basically what gives it its red appearance. Another aspect of the chromosphere are solar spicules, jets of hot matter that are in the chromosphere. Next, we go to the transition zone, which is not the twilight zone, but the transition zone, which is the transition between the chromosphere and the corona. Extends out to about 10,000 kilometers above the photosphere, above the surface of the sun. It's influenced by magnetic streamers and field, giving it its light and dark appearance through the transition. The transition zone will be subject to a very large change in temperature. As we got to the chromosphere, the temperature actually went down from the photosphere down to about 4,500 Kelvin. But from then on, in the transition zone, the temperature rises from that 4,500 Kelvin in the chromosphere to about 1,000,000 Kelvin. And this is fueled by the sun's magnetic field, and there's no mechanism really to take that energy away other than radiation. So it allows it to get very hot very quickly right above the surface of the sun. Leading up to the corona, which is starting off very hot as we see it here, at least 1,000,000 degrees Kelvin. And with that kind of temperature, boy, it'd be sure nice to have something cool, like a corona, to cool you down. Nah, that's not the solar corona. The true corona is the outer atmosphere of the sun that you can see during a solar eclipse. It's hard to see any other time, or difficult to see any other time, because the photosphere is so bright, and from our perspective, it would be almost impossible to see the corona. So you block it out through a solar eclipse, you can see the vast, beautiful outer atmosphere of the sun called the corona. It can only be viewed during a total solar eclipse. It's faint because it emits X-rays, not visible rays, and so we just have just a little bit in the visible range that you might be able to see, and because it's much less dense than the photosphere. So very dense, it's emitting light, mostly in the X-ray range, a little bit in the visible, and hence that would give you just enough for you to see in a total solar eclipse. Best chance, though, is to venture into the X-ray range and look at the solar corona from there. Here's another look at the solar corona. It's a region of extremely high temperature, up to about 3 million degrees Kelvin, predominantly in the X-ray range. Atoms are highly ionized and they emit radiation. And it is an emission spectrum, not an absorption spectrum, because the background is dark space. The particles are emitting radiation. There's no gas between here and there. So we're just getting an emission spectrum. So we would just see darkness with just a few bright lines in the spectrum from the solar corona. A lot of the information that we get from the sun is from the SOHO Solar Observatory. That is a satellite that is going around the sun, actually, and in somewhat of a synchronous orbit with the Earth. It is 1/100th of the way from the Earth to the sun, so it's still a lot closer to us, but it's focused on the sun at all times. And so a picture like this comes from SOHO, looking straight at the sun. The sun mainly has a predictable luminosity. It gives off this energy that we can count on, giving us a solar constant that allows life as we know it on Earth. But it also has some variability called activity. And this is associated with sunspot activity and magnetic flares and prominences from the sun. And so with these cycles of activity, we have predictable luminosity and activity with the sun. For instance, here is a picture of the sun in July of 1996, a basic, not very active sun giving off its basic luminosity. And then here, 5 years later, is a picture of the sun being very active at a very high point and with a lot of solar flares and activity, giving off bursts of energy at that time. Evidently, this is an 11-year cycle, so the next time that this would be this active would probably be around 2012. Minimum sunspot activity in 1996, maximum sunspot activity in 2001. More about sunspot activity in the next lecture. Here is a very active sun right here. The sun has what is called coronal holes, and these are holes that allow that are of very large magnetic fields that allow magnetic particles to escape, particles from the sun, and hence that is the major source of the solar wind that extends towards us. And we can see that this hole extends across the whole diameter of the sun. This particular one. So the solar wind escapes mainly through these windows of large magnetic field called coronal holes. This one looks, since Christmas season's coming up, this one looks like Rudolph, the red-nosed reindeer. Kinda. It kind of just fits in there in the image. So we have this increased solar wind that comes through the coronal holes. This one kind of looks like a face. This is the man in the sun. You can see like a mouth there and eyes here and maybe ears over here. Or maybe eyes here, nose here, and a mouth there. So it kind of looks like Jack Frost, yeah? Maybe. A little bit of imagination. Maybe not that Jack Frost, maybe the evil Jack Frost. The one, with the big mouth and the evil eyes and... Okay, too much time on my hands. But anyway, through these holes in the sun comes the solar wind. And that concludes lecture number 1 on the sun.